transporting SS7 over IP, SIGTRAN. I hope it will be a wonderful learning experience. All concepts and terminologies have been explained in detail. In order to support our efforts, it is requested to subscribe to our channel and press the bell icon for updates. Objectives. Upon completion of this tutorial, the student will be able to explain the role of SIGTRAN in core network releases, explain SIGTRAN's role in transporting SS7 messages, list and describe new terminology pertaining to SIGTRAN, diagrammatically represent the concepts of the SIGTRAN network model, describe the purpose and structure of Stream Control Transmission Protocol, SCTPs, explain the purpose and structure of MTP3 User Adaptation Layer, M3UA. Introduction. General. In telecommunication today, there is a greater drive to migrate all traffic generated in a network to packet-switched transport protocols. With the introduction of horizontal integrated networks, the first part of this migration to packet switching is realized. As we have already examined in previous chapters, the horizontal integrated network was defined into three different areas: the application layer, the control layer, and the connectivity layer. The whole concept of the connectivity layer was to provide the network with a common transmission platform from which to switch all call scenario types. That is normal speech, circuit switch data, GPRS, IP type calls, etc. In the beginning, the design of the core network structures utilized ATM as a common bearer transport technology when making circuit switched and circuit switched data calls using AAL2 bearers. As IP is considered to be a more efficient way of transporting information around a network, there is a push to have it as the primary transport mechanism. This signaling transport mechanism is referred to as SS7 over IP, or more commonly known as SIGTRAN. Signaling is a very important part of establishing, supervising, and releasing phases of a communication call. In the beginning, there are the signaling protocols introduced to do just that. When SS7 formalized, we utilized direct signaling connections to transport the signaling information. In this case, we were dedicating resources to the transmission of this information. In all forms of telecommunications, we required certain high-layer protocols implemented to perform certain tasks, whether they were for a fixed network, TUP, ISP, etc., speech calls, or for mobile networks, like MAP in GSM, realizing mobile-specific features, or when new features were added to growing list of services provided by an operator, like intelligent networks, mobile and fixed, or CAMEL, for mobile network only. These high layers had to have a common transport protocol to deliver them efficiently and reliably. In the beginning, the TDM network provided a 64 kb per second signaling link between two places, to also provided elements that could transfer on a link-to-link basis, signaling transfer points or STPs. This is traditionally known as narrowband SS7. Then afterwards, ATM was considered to be the common transport mechanism, given the role it plays in the connectivity layer. This allowed our signaling links to increase throughput to deliver larger amounts of data with a little less effort. Another benefit introduced was we no longer required to have dedicated resources to operate these signaling links. ATM allowed links to be established as needed, instead of allocating permanent resources. The use of ATM to transfer SS7 messages is known as broadband SS7. This increased the link from 64 kb per second to 2 MB per second, allowing an SS7 message to increase from a limit of 272 octets to 4096 octets. As IP networks become more extensive, the need to utilize the resources becomes more apparent. This is why we are now introducing the concept of SS7 over IP. Our existing SS7 protocols, high-layer protocols, used in telecommunication, can be merged into the same common transport mechanisms as speech and data traffic. This lecture will explain the concept known as SS7 over IP SIGTRAN. Traditional SS7 network structure. In figure we see that the traditional signaling network required a lot of resources and effort to maintain the SS7 network function. It did, however, provide the means of efficient and reliable transport, either as direct or link by link, of information. This was sufficient in the beginning. The main transport mechanism here is the traditional TDM transmission. To decrease the amount of hardware required sending and receiving SS7 messages around a network, STPs were introduced. The function of the STPs were to relay SS7 messages onto their correct destinations. Each connection is defined as a signaling link. These were maintained in link sets. It allowed routing SS7 messages route across a network promptly and efficiently. Proposed SIGTRAN SS7 network structure. In figure we see the general implementation of an SS7 network in core network. In implementing this structure, the main advantage of SS7 over IP is that we utilize the same IP backbone that speech, circuit switch data and GPRS to implement signaling as well. SIGTRAN terminology. Application server. As an application server is a logical entity that serves a specific routing key. This equates to the current high layers currently existing in SS7. For example, trunk switches use TUP, ISUP for setting up speech paths, using DPC/OPC/SIC_range. The HLR uses MAP for processing GSM/WCDMA locating messages, using DPC/OPC/SCCP_SSN. The MSC/VLR uses MAP and BSSAP for mobile mobility messages in the GSM/WCDMA networks, using DPC/OPC/SCCP_SSN. It relates to addressing the entity that will be processing the SS7 information. The AS is usually the reference used when a signaling node is using the signaling gateway to transfer SS7 messages to the terminating node. Application Server Process, ASP. An application server process is a processing instance in an application server. This equates to the process that it utilized in an application server. For example, the HLR processes location update messages and also handles the incoming call setup process. The MSC/VLR processes messages related to location updating, incoming call setup procedures, coordinating inter-MSC handovers and so on. An ASP can communicate through exactly one SCTP endpoint. IP server, IPS. An IP server is a logical entity that serves a specific routing key. It can be said that the IP server is exactly the same as an application server, except it is communicating point-to-point with the terminating node. The signaling is not using the signaling gateway to communicate with the terminating node. This equates to the current higher layers currently existing in SS7. For example, trunk switches use TUP, ISUP for setting up speech paths, using DPC/OPC/SIC range. The HLR uses MAP for processing GSM/WCDMA locating messages, using DPC/OPC/SCCP_SSN. The MSC/VLR uses MAP and BSSAP for mobile mobility messages in the GSM/WCDMA networks, using DPC/OPC/SCCP_SSN. It relates to addressing the entity that will be processing the SS7 information. The IPS is usually the reference used when a signaling node is not using the signaling gateway to transfer SS7 messages to the terminating node. IP Server Process, IPSP. An IP server process is said to be exactly the same as the ASP, except it is using M3UA in a point-to-point fashion. This equates to the process that it utilized in an IP server. For example, the HLR processes location update messages and also handles the incoming call setup process. The MSC/VLR processes messages related to location updating, incoming call setup procedures, coordinating inter-MSC handovers and so on. An ASP can communicate through exactly one SCTP endpoint. In this case, the nodes must be used in a point-to-point fashion for the IP server process to be realized. Routing key, RK. A routing key are a set of parameters and parameter values that uniquely identify an AS, IPS or SG. These parameters are derived from the same information in the MTP routing label. DPC/OPC/SIC range or DPC/OPC/SCCP_SSN. As we know that DPC has to be unique in the SS7 network, it cannot be defined in more than one node in the network. Routing context, RC. A routing context identifies a unique routing key or a set of routing keys. The routing context can be said to be a signaling route or a set of routing alternatives towards a particular AS, IPS, or SG. It is an identifier that indicates the particular AS, IPS, or SG that will be communicated with. SCTP endpoint. The SCTP endpoint is the logical sender/receiver of SCTP packets. It comprises of a set of transport addresses, a combination of IP addresses and port numbers, for sending and receiving SCTP packets between the two SCTP endpoints. These transport addresses must be unique to the SCTP endpoint throughout the network. This is very similar to the signaling point code of a node being unique within the signaling network. SCTP association. The SCTP association is the logical relationship between two SCTP endpoints. This association includes the protocol state information, verification tags, and the currently active set of transmission sequence numbers between the two SCTP endpoints. It can be said that the SCTP association is like the logical grouping of signaling links in traditional SS7, called a link set. A link set provides management towards a specific connection-orientated link. Signaling gateway. The signaling gateway performs the function similar to that of an STP in traditional SS7 networks, except it incorporates a conversion function, so messages from narrowband SS7, broadband SS7 and SS7 over IP can be converted between each other. There are two types of signaling gateway, an RSGW and a TSGW. The RSGW is referred to as the roaming SGW. Its functions are GT routing vs CCP relay, signaling conversions between SS7 and IP transport mechanisms, conversion between public and private IP addresses, and also conversion between IPv4 and IPv6. The TSGW is referred to as the transport_SGW. Its functions are signaling conversions between SS7 and IP transport mechanisms, conversion between public and private IP addresses, and also conversion between IPv4 and IPv6. SIGTRAN concepts. SIGTRAN node types. With the introduction of SIGTRAN, there are two basic node types. They are 1. IP signaling endpoint, IPSP. These are hosts in the IP domain that are the source and destination of SS7 messages. A SEP is the same as a signaling point in the traditional SS7 network, but connected to IP-based networks. IPSEPs have both signaling point codes and IP addresses. 2. Signaling gateway, SGW. The SGW has the function of receiving SS7 messages and converting them into the appropriate formats to send on through the network. As there are several ways SS7 message can be transported, either narrowband SS7, broadband SS7 or SS7 over IP. The SGW is usually co-located in the cello MGW. As the MGW is the node that sits on the edge of the core network, it must have the ability to signal to both traditional network structures and toward the proposed SS7 network structures. 3. With SIGTRAN there are still concepts that relate to traditional SS7 networks. The signaling transfer points, STPs, are replaced with IP routers to transmit SS7 messages across a network. But fundamentally the STP function is realized in nodes that utilize the M3UA protocol layer, SS7 routing function, to route towards the destination. Like in traditional SS7 networks, there are nodes that perform SCCP analysis throughout the operator's network. This is used when performing location updates whilst international roaming. This type of routing is performed on the SCCP protocol layer. Although the transmission technology has changed somewhat, the routing principles remain the same. SIGTRAN allows us to send SS7 messages over IP networks. There are 4 network scenarios implemented for SIGTRAN. These are 1. Signaling between two signaling endpoints, SEPs, inside an IP network. 2. Signaling between a signaling endpoint in an IP network and a signaling endpoint in a traditional SS7 network, TDM or ATM based. A signaling gateway is responsible to convert IP SIGTRAN messages into traditional SS7 messages. The two signaling endpoints may or may not belong to the same operator. 3. Signaling between two IP networks connected over a single SGW. 4. Signaling between two SGWs over an IP network. Each SGW is at the border of a network of an arbitrary network. SIGTRAN reuses some concepts of the traditional SS7 networks. The MTP addressing mechanism is the main concept reused. Other reused features are things like keeping track of signaling route and destination states. SIGTRAN model. SS7 protocol stacks. As we have seen in the previous chapters on MTP layers 1 to 3 and broadband SS7, SS7 over ATM, there are protocol stacks associated with the efficient and reliable transfer of SS7 messages across the network. In narrowband SS7, MTP layer 2 provides the reliability with error correction and detection. This was provided by SSNM in the ATM protocol stacks. In SIGTRAN we use a new protocol called Stream Control Transmission Protocol, SCTP. In narrowband SS7 MTP layer 3 provides us with the routing and network management functionality. For broadband SS7 the same functionality is implemented on the MTP3B layer. Whilst in SS7 over IP, this layer is known as M3UA. Figure illustrates the way the protocol stacks are implemented in MGW. These protocol stacks, or parts thereof, reside in all switches associated with all or part of SS7 SEPs. The two protocol stacks in figure refer to both narrowband and broadband SS7. The lowest MTP layer in narrowband and broadband refers to the physical transport medium. In our case, this is either SDH/PDH. Briefly, for narrowband MTP layer 2 provides the reliability of a message transfer using the traditional 64 kb per second time slot. The transmission medium was a dedicated physical resource, whilst the signaling link was in existence. MTP layer 3 provides us a mechanism to route an SS7 message throughout the SS7 network. This includes access to the high layers above MTP3, i.e. SCTP, IPSP, etc. For broadband SS7 the replacement for MTP2 is the SSNM process, which includes AAL5, SSCOP and SSCF. So this then provides the reliable transfer SS7 messages between two signaling points. This configuration provides us with a 2 MB per second signaling link on a physical ATM connection. The transmission medium was a shared resource that was shared amongst signaling and traffic payload. The MTP layer 3B provides us with the same functions as MTP3 of narrowband, except for larger message types. For example, an MSU in narrowband is a max of 272 octets. For broadband the max size of an MSU will be increased to 4096 octets. SIGTRAN protocol stacks. With the introduction of SS7 over IP, given the migration of signaling traffic over the same physical transport for user payload, there are a few protocol stacks that need explaining with reference to narrowband and broadband SS7 signaling. Below figure illustrates the protocol stacks for SS7 over IP. SIGTRAN protocol stacks. High layers. As illustrated in figure, the high layers of the SS7 protocol stacks are the same as previously discussed. These high layers are the specific application protocols used in mobile systems, intelligent networks, wireline networks, etc. These high-layer protocols include all the protocols for mobile solutions, intelligent networks GCP and BICC. M3UA protocol layer. The M3UA protocol is used in a similar manner to that of MTP3 and MTP3B. Its main function is to provide MTP routing for SS7 messages. It also provides a supervisory function, maintaining communication towards other nodes in the network. The M3UA protocol layer is responsible for providing the SS7-like signaling network function and features. The function and features provided by M3UA are to maintain routes and association states between peer M3UA layers of other nodes. M3UA also keeps track of adjacent nodes, routes and destination nodes. An operator defines these features manually, initially. It also maps their SCTP associations that connect to the different adjacent nodes. SCTP protocol layer. The SCTP protocol layer is responsible for providing the reliable connection between two IP signaling nodes. The signaling connection is established by means of an SCTP association. The Stream Control Transmission Protocol (SCTP) layer provides connection-orientated services between SCTP peer nodes by means of SCTP associations. These SCTP associations provide the reliable connection between two signaling endpoints. It offers acknowledged, error-free non-duplicated transfer of messages. The SCTP layer supports multi-homing. This is support for at least 2 local IP addresses. A robust SCTP connection. The concept also involves H/W duplication, so the SCTP connection supports full redundancy either in the node itself or in the underlying IP network. For a SCTP node to communicate with other SCTP nodes in the network, an SCTP association is defined. This association is created so each signaling point in the network that you will be communicating with is known to each other. The SCTP protocol checks the availability of the SCTP associations with the use of a heartbeat message. In the case of SCTP association loss, the time taken to detect this depends on the frequency of the heartbeat message. IP protocol layer. The IP protocol layer provides connectionless services between IP nodes. IP routers provide normal IP routing between sending and receiving nodes. The routing paths are established and maintained through the use of routing protocols like RIP, OSP, FBGP, static routes, etc. It is expected that the quality of service of the IP protocol layer is worse than the COS achieved in a SS7 network. Here, COS means, for example, network reliability, transmission time and recovery. Time after path failure. The COS provided by the IP protocol layer shall be enhanced through additional services provided from other SIGTRAN protocol layers, i.e. SCTP and M3UA. Stream Control Transmission Protocol, SCTP. As we have already seen, the SCTP protocol provides us with the reliable connection between two SCTP endpoints. The connection is supervised using the SCTP association established. Other functions that the SCTP protocol provides are connection-orientated message-based communication, independent message streams, multi-homing and a substitution for TCP protocol. As the SCTP protocol has been compared to the TCP/UDP protocols, there are similarities in how it functions. For a communication to occur through an SCTP association, the payload uses a transport address, a combination of the IP address and port number, to route the IP payload through an IP network. The port number mentioned is a unique IP port as defined at both ends. This requires that the same port number be implemented at both ends of the SCTP endpoint. The SCTP endpoint can be seen as the termination of the signaling stream. There is terminology associated with the SCTP protocol that explains a little about the protocol. SCTP association. The SCTP association is the logical relationship between two SCTP endpoints. This association includes the protocol state information, verification tags, and the currently active set of transmission sequence numbers between the two SCTP endpoints. Refer to figure. It can be said that the SCTP association is like the logical grouping of signaling links in traditional SS7, called a link set. A link set provides management towards a specific connection-orientated link. SCTP endpoint. The SCTP endpoint is the logical sender/receiver of SCTP packets. It comprises of a set of transport addresses, a combination of IP addresses and port numbers, for sending and receiving SCTP packets between the two SCTP endpoints. These transport addresses must be unique to the SCTP endpoint throughout the network. This is very similar to the signaling point code of a node being unique within the signaling network. The ports used by SCTP protocol are used in a similar manner to that of TCP/UDP. For example, if we look at the application Telnet, it uses IP as the transport mechanism, uses TCP as the transmission protocol, and is sent through port 23 to the Telnet application in the receiving end. SCTP messages and signaling procedures. The protocol data units of SCTP are referred to as SCTP packets. If SCTP runs over IP, then SCTP packet forms the payload of an IP packet. The transport addresses for the SCTP endpoint are in reality the source and destination addresses used as the header for the IP packets. SCTP signaling procedures. Let's examine the signaling sequences that are required to establish an association between two SCTP nodes. Below illustrates the most important SCTP message types to establish this connection. This refers to the originating node as the client and the receiving node as the server. To establish a connection we involve 4 SCTP message types. These are examined in below figure. There are 4 SCTP message types used to initialize an SCTP association. Figure 11-7 illustrates the sequence of signals required to establish the association. It begins with the INIT message, followed by the INIT ACK, then the cookie echo, and finally the cookie ACK. These messages and their formats, chunk formats, will be explained later. These messages will form chunks of the SCTP messages sent between 2 SCTP endpoints. Each message may contain several chunk types. However, it would be inappropriate to add certain chunks in a particular order within a SCTP message. For example, to abort an association we use an abort chunk. This chunk would not be bundled in with data chunks, as it is too short, or abort an association that is established. SCTP packet structure. An SCTP packet structure is composed of a common header and chunks. This is encapsulated inside an IP packet. This is illustrated in common header. The common header consists of 12 bytes. The source and destination ports, 32 bits to express the ports of the header, identify the specific association. In the SCTP header, along with the ports, there is the verification tag, 32 bits length, and finally the checksum, also 32 bits in length. The verification tag is a 32-bit unsigned integer that is randomly generated. It provides a key that allows a receiver to verify that the SCTP packet belongs to a current association and is not an old or stale packet from an old previous association. For the detection of transmission errors, the header implements a 32-bit checksum. Applied to the header only, it uses the ADLER32 algorithm. This is more robust than the 16-bit value checksum used in TCP/UDP protocols. Packets failing the checksum are silently discarded. Chunks. Following the header are a possible series of chunks. The number of chunks following depends on the maximum size of the MTU that can be carried. These chunks are carrying chunk-specific content. The first field presented is the chunk type, 16-bit expression. In reality, it provides us with the SCTP message types. These are introduced in chunk-specific flags. Follow the chunk type. There is a length field indicates the user data field, as it can vary in length. The final part is the user data associated with each chunk. The below two figures show us the SCTP_PDU and the SCTP chunk types. Chunk types. This section discusses the main chunk types and their formats. Each of the descriptions relate to an SCTP message chunk, which consist of a type, flags, length and then variable parameters. Chunk types and formats. Initiation, INIT. The INIT chunk is used to start the establishment of an SCTP association between 2 SCTP endpoints. Type. The type field indicates an INIT chunk. INIT flags. In an INIT chunk, these flags are all set to 0 by the sender and ignored by the receiver. Chunk length. This indicates the length of the data fields that follow. Initiate tag. The initiate tag is an unsigned integer that is generated at the sender's end, any value except for 0. The receiver records this and places it into the verification tag field of every SCTP packet that is transmitted in this association. Advertised receiver window credit. SCTP uses a sender-based credit procedure. The INIT chunk informs the receiver what size buffer is available to this association to begin. This value is and can be adjusted with the SAC chunk. Number of outbound streams. This defines the number of outbound streams to create within this association when established. Number of inbound streams. This defines the number of inbound streams to create within this association when established. Transport sequence number. The TSN is used to identify the sender's initial sequence number. To simplify things, it may be set to the initiate tag field value. The TSN is attached to each user chunk to permit the SCTP endpoint to acknowledge its receipt and detect duplicate deliveries. Optional variable length parameters. These parameters are optional and of varying length. For the INIT chunk, some of the optional parameters are IPv4 or IPv6, this is one of the SCTP endpoint addresses of the sending SCTP cookie preservative, reserved for explicit congestion notification capabilities, host name address and supported address types. In the case of multi-homed, the SCTP endpoint is allocated more than one IP address. These IP addresses would make an appearance in the optional variable length parameter field of IPv4 or IPv6. Initiation Acknowledgement, INIT ACK. The INIT ACK chunk is used to acknowledge the receipt of an INIT chunk at the receiving SCTP endpoint. It addresses the parameters that the initial sender requires to begin establishing the SCTP association between two SCTP endpoints. The parameters used in the INIT ACK chunk are the initial parameters from the receiving node of the INIT establishment of the SCTP association. The meanings are exactly the same for the INIT chunk, except they are the values replied to the sending node from the receiving node. The main difference is contained in the optional variable length parameters. They are state cookie. This is a parameter provides a message authentication code, timestamp on the creation of the state cookie, lifespan of the state cookie, and other information required to set up an association. IPv4 or IPv6, this is one of the SCTP endpoint addresses of the sending SCTP, unrecognized parameters. This parameter is only used when the sender has indicated that they want to be notified of unrecognized parameter information, reserved for explicit congestion notification capabilities. And host name address. The MAC is used as an integrity check mechanism. It is based on cryptographic hash functions using a secret key. This is initially added to the INIT ACK and allows the receiving nodes to validate the state cookie information. Cookie echo. The cookie echo chunk is generated and used by the sender of the original INIT chunk. It is used to complete the initialization of SCTP association. Cookie acknowledgement. Cookie ACK. The cookie ACK chunk is used to receipt the cookie echo chunk. This is the final stage to initializing an SCTP association. The format of the cookie ACK is only the type field, the flags field, and finally the length of chunk field. At this particular point in time, we have established an SCTP association between two SCTP endpoints. To complete the picture, there are other chunk types that need discussing. These are payload data. The data chunk is used to carry the end user's data between the two SCTP endpoints. Type. The type field indicates a data chunk. Data flags. The fields of the flags field are to say that the data chunk is unordered, beginning segment or end segment. Chunk length. This indicates the length of the data fields that follow. This indicates the number of bytes are in the chunk, starting with the type field and ends at the tail of the user data field. TSN. The TSN allows the SCTP endpoint to individually identify chunks. It also provides a means of acknowledging each chunk that is transferred. Stream identifier S. The stream identifier identifies the stream to which a chunk of user data belongs. Stream sequence number N. The stream sequence number indicates the sequence of the user data within the stream. Payload protocol identifier. The payload protocol identifier is used to identify the particular application that the data is processed by. This information is not used by SCTP, but is mandatory for uses in the high layers above SCTP. For normal operation, SCTP is required to manage the established connection. To do this, SCTP uses heartbeat and heartbeat ACK chunks. Heartbeat request, heartbeat. The heartbeat chunk is used to probe the reachability of a destination transport address, defined in an established association. The heartbeat information field contains the sender's current time and the destination transport address. Heartbeat acknowledge, heartbeat ACK. The heartbeat ACK chunk is used to respond to the heartbeat chunk. It contains the receiving peer's heartbeat information. The heartbeat information field contains the sender's current time and the destination transport address. This was the source IP address of the heartbeat request chunk. The last chunk type to look at is one that allows us to be able to selectively acknowledge chunks that have been received so they can be cleared from the buffers. Selective Acknowledgement, SAC. The Selective Acknowledgement chunk is used to provide acknowledgement on received data chunks. It also provides a mechanism that provides information about gaps in received data chunks. This is provided by the acknowledgement using the TSN numbers allocated to the data chunks containing user data. Type. The type field indicates in SAC chunk. SAC flags. In and SAC chunk, these flags are all set to 0 by the sender and ignored by the receiver. Chunk length. This indicates the length of the data fields that follow. Cumulative TSN acknowledgement. The value for the cumulative TSN acknowledgement is that of the TSN values up to the first missing/corrupted break in a sequence. The parameter therefore acknowledges receipt of all TSNs less than or equal to its value. Advertised receiver window credit. SCTP uses a sender-based credit procedure. This is used to update the status of buffers in the receiving node. Number of gap-ACK blocks. This defines the number of gap-ACK blocks included in this chunk. Number of duplicate TSNs. This defines the number of duplicate TSN blocks included in this chunk. Gap-ACK block start and end. These fields allow the SCTP to indicate where a gap has occurred in the received information. Duplicate TSN. These fields are to indicate which TSNs are duplicated at the receiving end. Congestion and flow control for SCTP. The SCTP protocol implements congestion and flow controls for an established association. General concepts. SCTP distinguishes different streams of messages within one SCTP association. This enables a delivery scheme where only the sequence of messages needs to be maintained per stream. Detection of loss and duplication of data chunks is enabled by numbering all data chunks in the sender with a so-called transport sequence number, TSN. The acknowledgements sent from the receiver are based on these sequence numbers. Retransmissions are timer controlled. The timer duration is derived from continuous measurements of the round-trip delay. Whenever such a retransmission timer expires, all unacknowledged data chunks are retransmitted, and the timer is started again, doubling its original duration. When a receiver detects one or more gaps in the data chunks, each received data chunk is acknowledged by sending a selective acknowledgement, SAC, which reports these gaps to the sender. Whenever the sender receives 4 consecutive SACs reporting the same data chunk missing, this data chunk is immediately retransmitted. This method is known as fast retransmit. Flow control. SCTP uses an end-to-end window-based flow and congestion control mechanism, similar to that of TCP. The receiver of data may control the rate at which the sender is sending by specifying an octet-based window size, referred to as the receiver window. This value is returns in SAC chunks. The sender itself keeps track of a congestion window that controls the maximum number of outstanding bytes that are buffered before acknowledgement. Each received data chunk must be acknowledged, and a receiver may wait a certain time, usually 200 milliseconds, before that is done. Should there be a large number of SCTP packets containing data that should be acknowledged at once by sending a SAC chunk to the sender. Selective acknowledgement. The SAC chunks allow us to provide acknowledgements towards the SCTP endpoint. Setting the cumulative TSN ACK value does this. This value indicates that the data chunks received have been successfully received and are moving toward the upper layers above SCTP. Along with this parameter is the gap block indication. These indications inform the sender that there is certain data chunks received and also which ones are missing in between. There are 2 ways that the data chunks are retransmitted. The first is after the retransmit timer expires, normal operation. Or secondly, when there are 4 consecutively received SACs indicating the same data chunks missing. Multi-homed endpoints. Multi-homed endpoints are SCTP endpoint that terminated multiple IP addresses in an association. All transmission is done to a previously selected address from a set of destination addresses. The IP address used is referred to as the primary transport address. Retransmissions should be done on different paths, so that if one path is overloaded, retransmissions do not affect this path. The acknowledgement chunks are always sent to the transport address used in the originator's data chunks. Should the active path have a high number of failures and its error counter exceeded, the SCTP implementation notifies the upper layer processes that the path has become inactive. The upper layer processes then select another path to send the signaling information. The INIT chunk informs the SCTP endpoint of the list of possible SCTP transport addresses that are recognized in an association. The receiver then returns its list in the INIT ACK chunk reply. Hostnames can also be used as transport addresses. Congestion control. The SCTP implementation controls the congestion behaviors that affect the timely delivery of messages between the two SCTP endpoints. For each destination transport address, there is a discrete set of flow and congestion control parameters kept. Given the transport network is all IP, the IP routers will adjust paths to cater for IP network abnormalities. Slow start and congestion avoidance. SCTP implementation operates in two modes, slow start and congestion avoidance. In normal operation, the mode is determined by a set of congestion control variables that are path-specific. The primary paths usually operate in congestion avoidance mode, whilst slow start is used on backup paths. For successful delivered and acknowledged data chunks, the congestion window variable is steadily increased, and once it exceeds the slow start threshold, the mode changes from slow start to congestion avoidance. Peer-to-peer monitoring. The SCTP endpoints need to monitor their SCTP association to make sure that it is always available for signaling. Link activity is monitored by the use of heartbeat chunks. The reply to a heartbeat is the heartbeat acknowledge. The heartbeat chunks are sent over all paths toward the peer instance in an SCTP association that is not currently carrying data chunks. Each path is assigned a state, either active or inactive. A path is considered active if it has transmitted a SCTP packet towards its peer and received acknowledgements for its data chunks. If the transmission path repeatedly fails to deliver reliable information, the path is designated inactive, and the high layers are informed, so the application then selects another path to transmit data chunks. Path selection. SCTP protocol selects a path as primary when it is establishing the SCTP association. The data chunks are sent over this primary path by default, whilst ACK chunks, SAC chunks, retransmissions, another active path is used. To support the continuous measurements of round-trip delays, SAC chunks are sent to the source address of the SCTP packets, which carried the data chunks. The layers above the SCTP protocol are informed about the status of each path when there is a request or when the path changes from active to inactive, and vice versa. Notification service primitives. The SCTP protocol uses service primitives to notify the upper layers of SCTP association status changes. In all, there are 8 service primitives. These are explained below. Data arrive notification. This is used when SCTP invokes the notification to the upper layers when a user message is successfully received and ready for retrieval. Send failure notification. This is used when SCTP shall notify the upper layer that a message could not be delivered. Network status change notification. This is used when a destination transport address is marked inactive, e.g., when SCTP detects a failure, or marked active, e.g., when SCTP detects a recovery. Communication up notification. This is used when SCTP becomes ready to send or receive user messages, or when a lost communication to an endpoint is restored. This is the case when an SCTP association is considered established. Communication lost notification. This is used when SCTP loses communication to an endpoint completely, e.g., via heartbeats, or detects that the endpoint has performed an abort operation. Communication error notification. This is used when SCTP receives an error chunk from its peer and decides to notify its upper layer. Restart notification. This is used when SCTP detects that the SCTP peer has restarted. Shutdown complete notification. This is used when SCTP completes the shutdown procedures. MTP3 User Adaption Layer, M3UA. General. The M3UA layer services provide the SS7-like signaling network component of SS7 over IP networks. It provides the same connection-less services that are used by traditional narrowband SS7, MTP3 and broadband SS7, MTP3B provide. For usual implementation of SIGTRAN, there are 3 types of signaling point: the signaling endpoint, SEP, the signaling gateway, SGW, and signaling transfer points, STPs, like in traditional narrowband SS7 and broadband SS7. The signaling endpoint is fairly self-explanatory. These are the endpoints that build and analyze SS7 messages around the communications network. However, the function of the SGW is to interface the three types of SS7 network together. This allows for converting a narrowband SS7 message into an SS7 over IP message. The M3UA layer provides us with the same sort of services that MTP3 does for narrowband and broadband SS7. That is, a signaling point code is allocated to a node along with a network indicator. The M3UA protocol main functions are as follows. 1. Maintains the M3UA associations and their states. 2. Maintains M3UA routes and their states. 3. The availability of destinations. 4. Maintains the availability and connectivity of the local SCTP layer. It also provides -1. Mapping between IP addresses and signaling point codes. 2. Configuration of signaling routes between local and peer nodes. 3. Provides redundant routes to destination nodes. M3UA terminology. M3UA association. The M3UA association is the representation of the SCTP association in M3UA layer. M3UA maintains variables relating to established associations. For flow and congestion control, M3UA assigns states to each of the established associations. M3UA route. The signaling route in M3UA is the same as the MTP routing for both narrowband and broadband SS7. A route identifies an outgoing association that can be used to send data towards a specific signaling destination. The route information is combined between an association and a signaling destination. M3UA route set. The M3UA route set is a collecting of all alternative routes toward a specific signaling destination. If the route set is not available, then a destination is considered to be unreachable. M3UA signaling destination. The M3UA signaling destination is a node that can be signaled to. The use of a SPC is used to identify a signaling destination. It is referred to as the DPC of an outgoing message. The sending node doesn't know if the receiving node is an SS7, traditional narrowband or broadband, or an IPSP, IP signaling endpoint. M3UA messages and signaling procedures. The protocol data units of M3UA are referred to as M3UA service primitives. M3UA manages the set of service primitives that are transported via the SCTP protocol. Therefore, if SCTP runs over IP, then the SCTP packet forms the payload of an IP packet. The transport addresses for the SCTP endpoint are in reality the source and destination addresses used as the header for the IP packets. M3UA protocol service primitives are encapsulated inside the SCTP payload packets. M3UA signaling procedures. Let's examine the signaling sequences that M3UA uses to establish an M3UA association between two M3UA peers. M3UA uses the SCTP protocol to transfer its messages to the remote destination. Below illustrates the most important M3UA message types to activate an M3UA communication. To establish M3UA connection activation, we involve 4 M3UA message types. These M3UA message types are examined in figure. The associate establishment procedure is described in figure. The process is described below. 1. M3UA sends an associate primitive to the SCTP instance. This primitive contains the association ID, the destination IP address and outbound stream count. 2. The SCTP protocol then uses the INIT chunk to establish an SCTP association between two SCTP endpoints. 3. The receiving SCTP entity then responds with an INIT ACK chunk. 4. The initiating SCTP entity then forwards a cookie echo chunk. The information transferred is described in figure. 5. Then the receiving SCTP entity responds with a cookie ACK chunk. This chunk is always used to acknowledge a cookie echo once it is received. 6. Once their SCTP entities have established their associations, then SCTP at both ends send the communication up primitive to the M3UA layers. This indicates that the M3UA layers can communicate peer-to-peer now. The communication up primitive is used by the SCTP protocol to indicate that it is ready to send or receive information between two SCTP endpoints. 7. The M3UA layer sends an ASP protocol message towards its peer M3UA layer to indicate that it is ready to receive any messages from the peer. This message is a state maintenance message. 8. The receiving M3UA layer responds with an ASP protocol message. It is used to acknowledge the receipt of the ASP protocol message. This message is a state maintenance message. 9. From here the originating M3UA layer will send an ASP activate protocol message. The M3UA layer to indicate to its peer M3UA layer it is ready to receive signaling messages uses this message. This message is a traffic maintenance message. 10. Once the ASP activate message is received by the M3UA layer will respond with the ASP activate ACK message. This message is a traffic maintenance message. 11. Finally, the data to be sent is sent across the active association between the two M3UA peers. M3UA packet structure. The M3UA packet structure is composed of a common header and variable length parameters. This is then handed down to the SCTP protocol to be transported towards the destination. Common header. The common header consists of 8 bytes. The first byte defines the M3UA protocol version, currently version 1.0. The following byte is reserved, set to all 0s. The next byte to follow defines the message class, then the message type. The last 4 bytes indicate the message length. Variable length parameters. Following the common header are a possible series of parameters. The number of parameters following depends on the message type and class. These parameters consist of a parameter tag, parameter length and the actual parameter value. M3UA message classes and types. The M3UA protocol consists of 5 allocated classes. Each class then has a number of types defined. Each message class will define several message types. Messages classes are defined as follows. Messages types are defined as follows. M3UA transfer message, data. Below figure is an example of the message class transfer message type payload data message. The payload data message consists of a common header. The common header defines the version of the M3UA layer, and then comes the message class. This should be set for transfer messages. Following this is the message type. This should indicate payload data message. The last field in the common header is the message length. This value indicates the length of the message in octets. This value will include the common header as well. As is the format for IPSP, SCCP, the structure of the payload format depends on the message types. In the case of an M3UA transfer message, there are defined parameters that are either mandatory or optional. As designed in specifications, the payload data message has 4 parameters possible. The only mandatory parameter is the protocol data. This is the payload of signaling traffic. The remaining 3 are all optional parameters. There are the 1 network appearance, 2 routing context, 3 correlation ID, M3UA management, congestion and flow control. M3UA supports services that provide state management, congestion and flow control. There are 3 groups of message classes that assist in the implementation of state management, congestion and flow control. These are the :1. SS7 signaling network management messages, SSNM. These are messages that allow the M3UA layer to manage an active link association between 2 nodes. These mainly maintain the status of configured destinations and route messages, according to availability and congestion status of routes towards these destinations. This also maintains the message routing availability information. This is used in a similar way to those used in traditional SS7 network management messages. 2. ASP state management messages, ASPSM. These are messages that allow the M3UA layer to manage state of M3UA layer peer associations. These messages relate to the management and state changes between 2 nodes. 3. ASP Traffic Management Messages, ASPTM. These are messages that allow the M3UA layer to manage state of M3UA layer peer associations. These messages relate to the communication of state changes between the two nodes. M3UA and MTP3 mapping of messages. It is important to remember that there is support for the three implementations of SS7 transport functions: narrowband SS7, broadband SS7 and SS7 over IP. We must remember that the signaling gateway is an important part of the core network infrastructure. It must have the ability to be able to convert SS7 messages into either of the three formats. M3UA, MTP3 short message description. I hope it would have been a wonderful learning experience. All concepts and terminologies have been explained in detail. In order to support our efforts, it is requested to subscribe our channel and press the bell icon for updates. Stay tuned. Thanks.